All righty. Get up and running here. Got a board. I want to introduce two new calculations. Get the conversation started. Try to keep it pretty simple at the beginning here. And the reason I'm doing it is this will lead us into something that students notoriously have trouble with. A topic, I don't want to say the topic quite yet, but people don't have much success with it. And I think it's because it's takes a little while to understand. And we're going to go at it piecemeal. We're going to build up to it so that during the second half of the semester, we'll practice with it a lot and hopefully get some working knowledge in that area, which is a whole lot better than having no working knowledge in that area. And that's what I'm seeing coming into my classes at the higher levels. So we want to avoid that. So the first thing we're going to do, I'm going to give you a little problem here, and we're going to do 4 or 5 in a row, similar problem, and then I'll include it in a worksheet tomorrow, and you can try it. Then we'll just continue to put 1 or 2 problems on the worksheet, add 1 or 2. I was very pleased with what I saw today. Saw some movement in the right direction. And when you do tomorrow's worksheet, I'm hoping that the problems that you got right today, you recognize maybe a little more quickly, maybe a little more confidence with it, and that's the process. And if we keep doing that, we're going to build some skill and keep talking about what's going on and why. And it's going to take some time, but I'm hoping that within 3 weeks or so, you feel very comfortable with the process because I'm still kind of overloading it. All right, so still a lot of stuff we're doing is algebra 1 that just didn't sink in. We got to get it to sink in and then build off it. So, can you perform this calculation? Right. So this is a base, and you are performing this. It's telling you to do something. It's asking you to do 3 things, actually. It's asking you to do 3 things, and I want you to identify what those 3 things are and be able to work with them. Right? So the first thing that you're supposed to do, or you can do, is something that I think you know, 4 to the 3. 4 to the 3, that's built in there. I think you know what that means. I think you know that that's 4 times 4 times 4. And 4 cubed is actually 64. So if I perform that operation, 4 to the 3, I get this number. I still have those 2 operations. All right. We did talk about this one briefly, and we actually did talk about this one briefly, but you know, that was Monday. I bet you already forgot that conversation. And I would say you probably have to, you know, work with us a couple of days before you're going to have some confidence with it. So don't hold yourself responsible for not being able to answer that question. This, we talked about 1 over 5 squared on day 1 as being equivalent to 5 to the negative 2. All right, so 5 to the negative 2 is really 5 over 1 to the minus 2, and that becomes 1 squared over 5 squared. In other words, minus 2 means that you have 5 times 5 in the denominator. Minus 3 would mean that you have 1 over 5 to the 3rd power. 5 times 5 times 5. Okay, so this negative sign means things are occurring in the denominator. So we really have a minus sign. Okay, and that means that this 64 is really in the denominator. That means I only have 1 more operation, that 2. What we talked about on Monday was, I think the example I gave you was 5 squared. Everybody knows is 25. What's 5 to the 2 over 2? Well, I just canceled squaring, right? That undoes squaring, and so that came back to 5. So squaring on the left side of the equation is the same thing as square rooting on the right. So what I'm basically saying is that means square root, that means flip, and that means cubing. So let me just do 4 or 5 in a row of that topic. And let's see if you can identify what you're looking at. And then I'll come back to this. I'll come back to this problem because there's a whole lot easier way to do this than what I just described. All right, but let's just do those three operations and let's see how you do. All right, 2 cubed. You pause the video each time. Say, okay, 2 cubed is just 8. 2 times 2 times 2. Okay. 25 to the 1/2. Yeah, well, that's a square root. The square root of 25 is 5. So that is the same thing as saying this. Those are identical statements. 3/7 to the -1. Well, that negative sign really is about reciprocation. So that's 7/3. All right, now let's put it all together with this problem here, which we know the answer to. The answer to this was 1/8. All right, so how do we get there? Well, you got 3 operations. This one here is reciprocate. You can think of it as flip the base. Now, the base right now is 4/1. I don't want to flip the base right now because that means I'm working with fractionally, and it's much easier to not work with fractions. So I have a choice now because order doesn't matter. I can either cube 4, which is what we did before, 4 times 4 times 4, 64, right? And then I could take the square root of 64, which is where the 8 came from. But why don't I take the square root first? Okay, so if I was doing this problem, I would do it in this order. I would say, okay, I know the square root of 4 is 2. So I got to do 2 to the -3, and I know that's 1/8. I know that's 1/2 cubed. Okay, because this is really a fraction. So why don't I cube? I would just, at this stage, I hope 2 to the -3, I hope you would know is 1/2 cubed, put it in the denominator, and then you get your 1/8. So let's try a couple of those for you and see how you do. Let's do 8 to the -2/3. You're pausing the video. I'm looking at this and going, I'm going to do this first. And that's a cube root. And the cube root of 8 is what times what times what gets you 8? 2 times 2 times 2. So what's the cube root of 8? 2. So I'm going to do the cube root of 8 is 2, and that's 2 to the -2. Well, I know that's 1/4. Okay, let's do 1/16 to the -3/2. Do 1/16 to the -3/2. Well, in this case, I'm going to flip it right away. I'd rather work with an integer. So that's the same thing as 16 to the 3/2. Now I can either do the square root of 16 times 16 times 16, or I can do the square root of 16 and then cube it. One of those is easy. Darn right, I'm going to do the square root of 16. 4 to the 3 from earlier work, we know 4 to the 3 is 64. Okay, so that gets us started with identifying some exponential activity, and I'll put one of these on your worksheet tomorrow. I'm already writing it. I'll just add it to the list. We'll see if we get to it. Maybe I'll put it in the beginning. Let's see, tomorrow. No, I'm actually assigning this after tomorrow's. I'm assigning this. I'm going to put it out there tonight. Anyway, you're going to see this at some point. Now, I normally start all of my Algebra 1, Algebra 2, and pre-calc classes with the following. Math is a language, so I'm going to write it out. The value of the exponent that you put on top of a 2, no, on top of a 5, that you put on top of a 5 to get 25 is a 2. Now, I don't know if we did this or not. I'm pushing up there in age, and my memory is terrible. There's a little bit of me that thinks we did this. It doesn't hurt to do it again. Reps are everything in math. So what would you write? The value of the exponent put on top of 5 to get 25 is a 2. Now, maybe we did it. If we did, I'm sorry, but most people say 5 squared equals 25. Right? But it's not what I wrote. What I wrote was, and if this is how we do math, we're in big trouble, right? That took me too long to communicate to you. Just too long. If that's how I had to do math, write it out with English sentences and words, I'm done. I'm not doing this discipline. That took a lot of effort. I'm tired. So, the value of the exponent, that's what the word log represents. That's a log, logarithms. I think it was in the early 1600s, a guy named Napier developed logarithms, and those log tables allowed people like Kepler and Enlightenment period to work with big numbers, because this is going to help us work with big numbers, and they didn't have computers back then. To put on top of a 5, that's where the base goes. To get 25 is a 2. Now those are the same numbers, right? And so when you see the word log, you're basically saying, what do I put on top of a 5 to get 25? And we know that. Okay? So in essence, what you're really trying to do is you're trying to write the number 25 in base 5 notation, and then you're looking at the exponential activity. That's how we're going to work with these things. Now I'm going to give you 5 or 6 examples. We'll see how we do. Now, first off, let's go back to this. Five to the 2 is 25. This is your exponent. This is your quantity. So therefore, this is your x, and this is your y when we start doing exponential equations. Well, over here, this is your x, and this is your y. So on this side of the board, for 5 to the x as an equation, a 2 gets you 25. Let me see if I can show that. And 5 to the x, a 2 gets us 25. Over here, this is the calculation. Okay, and if I write that one in table form, log base 5x, if I start with a 25, I get a 2. Those are inverses. Where have you used inverses so far in the first week? Only 2 days of class. Where have you used inverses? Solving equations. So if you want to solve an exponential equation, you got to put it in log form. And if you want to solve a logarithmic equation, you got to put it in exponential form. That's the first time you heard that. You may need to hear that 20 times before the lights go on. All right. So let's do some log work now. Log. Let's put an 8. Now let's put an 8 there, and let's put a 2 here. Now, how would we do that problem? Well, log means I'm looking for the exponent on top of an 8. That gets me a 2. Well, those aren't the same base. They're not the same base. I'm stuck. Is there a way to write 8 in base 2 notation? Oh, yes. 8 is 2 cubed. And that's being raised to the x power. And I want that to equal 2 to the 1. Well, I hope you know what you're supposed to do with that exponential activity. You multiply. So 2 to the 3x equals 2 to the 1. So therefore, if the bases are the same, the exponential activity has to be the same. And therefore, x is 1/3. Okay. So the exponent is 1/3. And that brings us to exponential form to check it. Is that a true statement? We just worked with that 10 minutes ago. What does this mean? It means the cube root of 8. Is the cube root of 8 2? By golly, it is. So that's what you would have done to figure out what that equals. Let's try another one. Let me try some easier ones first. And I just looked at an exponential rule, and I don't trust that you all know that rule, so I want to make sure I develop it. Let's look at x squared cubed. That means I have something times itself 3 times. What is going to be multiplied 3? X squared. What is x squared? It's x times x, and that's times x times x, and that's x times x. And that's x to the 6. Count them up. So I hope you now know what the rule is when you see power to power. So let me give you a bunch of logs that are hopefully stuff you can connect with quickly. I think the first one I did might have been too hard. Okay, so what's 125? 125 could have been written as 5 to the 3. So what's the exponent you put on top of 5 to get 5 to the 3? A 3. Try another one. Log base 2 to get 32. Let's see, well, 32 is 2 times 2 is 4 times 2 is 8. 16. Oh, geez. I can do 2 to the 1, 2, 3, 4, 5. That's the exponent that you put on top of a 2 to get 32. That's what we're looking at. And let's see. Can I get you to do log base 4 of 1/16? Now you pause the video. Well, what's 16? 16 is 4 squared. Where's the squaring occur? In the denominator. How do I communicate that to you? -2. 4 to the -2 is equal to 1 over 4 squared, which is equal to 1 over 16. Let's do one more. And the reason we're not working with the 4th root of 16 that way is there's history to this discipline. And the early computers didn't like radical symbols. They're called radicals, square roots, cube roots. I didn't, but now, you know, we're doing a lot better with computers. People can use these symbols now. But earlier work, some of the IBM equipment and whatnot, work with numbers. So you want to look at 4 to the 1/2. Well, maybe not that one because that's a 2. I don't want anybody thinking you're cutting 4 in half. 4 to the 1/2 means the square root of 4, which is 2. Okay, but the numbers were more user friendly for the machines. All right, so one last one. We'll give you a kind of a tough one. 4 to the 8. Okay, so how do you rewrite the first line of work? Hey, I got to find the exponent that turns a 4 into an 8. Now, with practice, some of you are going to be able to do those without doing any work. You're just going to know. You're going to know that you want to take the square root of 4. The square root of 4 is 2, and 2 cubed is 8. Be nice to get there. That's your ultimate goal. But how do we get that answer when we're here? We got to get the same base. And I hope you can see that, you know, 4 and 8 are multiples of 2. Or factors of 2. I'm not sure the word I want to use there. I'll think about it later because it's getting late in the day and I'm getting tired. All right, so 4 is 2 to the 2 to the x. 8 is 2 to the 3. Again, we come back to power. We just talked about the rule. Same base, which means that has to equal that. So 2x equals 3, and x equals 3 over 2. Oh, yeah. That's a good one. All right, and while I'm here, I might as well give you a little bit, one more thing to think about, because it's already on the table. I'll just try to layer our understanding a little bit more. All right, so this is a rectangle. I'll call it x plus 2 times x plus 6. All right, so x plus 2 times x plus 6 is factorable, and it's x squared plus 6x plus 8x, sorry, plus 8x plus 12. Right, if you foiled it. If you foiled it, you got x times x plus 6 And you got 2 times x plus 6. And I hope if you pause the video a moment, you see how this morphs into that. I've got 6x and 2x, which is the 8x. I've got x squared, and I got just 2 times, did I say this right? X and x plus 6, yeah. So 2 times 6 is 12. All right, not quite sure. Yeah, fine. So I should have done this. I haven't done this too much. Just in case anybody missed this from your Algebra 1 experience. And I could do more diagramming there, but that's enough for now. All right, so what would happen if I set this to 0? Well, I'd have to be able to do this. I'd have to be able to see the critical numbers, -6 and -2. -2 plus 2 is 0. You get rid of the dimension of a rectangle. Like I'll use -2. -2 gets rid of the height. There's no area. There's an area statement. So you got to come up with something. All right, so what do we come up with? We know this is a rectangle. And this is called factoring. We solved that by factoring, which, yeah, see what kind of experience you've had. You're supposed to be able to do it already. I'm not sure you have the ability to do it. We'll find out. So what mathematicians did centuries ago was they reconfigured this into a square. And then, of course, reconfiguring it was x plus 6, it was x plus 2. So you make the longer side shorter, and you tack it on here, which gives us a new amount. Then you make the shorter side longer. Well, that's not the same thing as this anymore. This is now x squared plus, well, I've got to make this 4, right? It is getting late in the day. I'm tired. You can see my brain's starting to go into shutdown mode. So if I added 2, took 2 away from 6, added 2, this is now a square. All right, so let me use that over here. Let's do, oh yeah, I'm really tired. X plus 4 times x plus 4, and let's go back to what it was originally so that I can clear up confusion because I really didn't say this well. So what I've done is I've taken away 2 units here, made it there, reshaped things. So we know that when we multiply this, we get x squared plus 8x plus 12. If we multiply this, take more time if you want, you get x squared plus 8x plus 16. I gotta put that there. There's a funky looking square. They're pretty darn close. And if I want to maintain this equality numerically, I can subtract 4 on the outside of that, and that keeps track of the area here being the same area here. In other words, I could put any number in here, use the same number over here, and they are going to be equal. Let's put 10 in here. 180, 192. When I put the number x equals 10, would have been easier for me to put it here, right? Maybe not. 12 times 16, no, I think I'd rather do it there, but I get 192 units of area when I put in 10. Let's do 10 over here. Well, that's 180, 96. That's 196, but I'm subtracting 4. They are the same. Okay, so now why am I doing this? Because symbolically, I can write what's over here as x plus 4 squared. I don't have to draw the square. I can communicate it to you like that. Minus 4. And you've seen that before because you now know the vertex of this parabola. You now know it is minus 4 minus 4. Right? Now, I have 2 ways of solving. So let me get over here and talk about the graph. What happens when I see this? When I see that, I see this cup shape up, -4, -4. I don't immediately see that over here. What I see over here is x plus 6 times x plus 2. And when I see that, I see what makes zeros. What makes zeros is -6 and -2. And then I have this. Okay. They're the same graph. In other words, if I want to find this, then I've got to use the number between -6 and -2, which is, oh, -4. And if I put -4 in here, it's easier to put it here. These numbers are smaller now than here. -4 plus 6 is +2. And -4 plus 2 is -2. And 2 times -2 is -4. They're the same calculation, just expressed differently. So I look at them, I look at the parabola from a different perspective. Now, -2 gets me 0. I want the y-intercept. Well, the y-intercept is when x is 0, so I could put it in here, and I could see that a 0 gets me 12. I can immediately see the y-intercept here. I gotta plug 0 in over here. And 0 plus 4 is 16, minus 4 is 12. It's the same calculation. But I'm doing different things at different moments based on the language I see. I want you to have that experience, and you got until May 15th. It's in front of us. We'll just work with it every day. Now, there's one other thing that really is helpful. How do we solve these equations when we want to know, let's say, equals 0? Well, let me change this number slightly. Let's go to 13. What was it before? 12? Now it's 13. So I guess I think it's -3 now. I think that's the same, but let's just check it with 10 again. So 10 gets me 193. 14 squares 196 minus 3. Yes, so I've got that right. Okay. How would you can't factor this. So what did you learn in algebra 1 to do that? You might not know. You learn the quadratic formula. And I haven't used the quadratic formula in years because there's easier ways to do things. X squared plus 8x plus 13. We just started talking in class about what to get the x value of the vertex. I doubt you remember. Maybe you do. If you do, good for you, because you haven't heard it that much. Minus b over 2a. Remember, I put a 0 here and a minus b over a here. Drew a little parabola and said, well, the average is minus b over 2a. These are x values. And what is minus b over 2a? It's -8 over 2. The number in front of x squared is 1. And there's your -4. What do you do to find the y value? You plug -4 in here. And -4 plugged in is 16. -4 times 8 is -32. And 13. And that's -16 plus 13. Which is -3. Oh yeah, you just write it there and it's the same calculation. All right, what's the advantage? Oh, this is a piece of cake. That's a piece of cake. What do you do first? Move 3 to the other side. It's gone. What's the next thing you're going to do? Undo squaring. Plus minus square rooting. Right? Why the plus minus? Here's x squared. Here's a height of 9. -3 squared is 9, and so +3. Negative numbers act just the same way as positive. That's what we did in class this morning. And so negatives, just the same things as positives. So you're gonna have to remember that. Good luck. The only way I ever got people to remember it was to sneak up behind them after 2 weeks of saying 2 weeks from now, if you forget the plus minus, I'm gonna sneak up. I'd sneak up and I'd right behind somebody and scream. Whole class would jump. And unfortunately, I did it to a kid with a concussion once, so I never did it again. All right. Didn't know. He's a buddy. I'm glad he was a soccer player and I knew him well. So yeah, he was very forgiving, but can't do it anymore. So you got to remember on your own. I haven't had any class very good at remembering it on your own. Maybe you will. All right, so I moved the 3. It's gone. I moved the squaring. It's gone. The only thing I got left is -4. Addition of 4. Okay, and that x value is x-intercepts, where the parabola hits 0. I'll show you how it hits 0. I can't show you here easily, not yet, but I can show you over here easily. So we had, and just this will be the last thing I do. I've overloaded you enough. So x plus 4 squared minus 3. We're going to see what happens when I replace x with -4 plus or minus the square root of 3. -4 plus or minus the square root of 3 minus 3, and we're going to see what that equals. Oh, I forgot to say plus 4. Squared minus 3 there. Now we're up to speed. Do you mind if I do -4 and +4 right now? Is that okay if I do that? -4 plus 4, I mean, that equals 0. So I just erase it. What happens when you square a positive or a negative? Well, positive times a positive is a positive, and a negative times a negative is a positive, so you can ignore that too. What do you get when you square the square root of 3? Let's see. That area is 3. I think that's a square root, the side of a square. I got a feeling that if I take that and multiply it times that, I'm going to get 3, because that's what that is supposed to be. The number times itself that gets you 3. I hope you can see if I put the square here, you got inverse operations. And you get what's inside. It worked. We found out what made it equal 0. There's still lots to talk about here, but we're getting at it. See you tomorrow in class. And this isn't really due until, I guess I can't ask you to do a log or an exponent until Friday. So this is going to be Thursday night's assignment. Okay, end.